Hello. In this podcast, we'll be exploring Newton's second law of motion. Specifically, we're going to look at second law basics, talk about weight, apparent weight, and a problem-solving strategy for using Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Mathematically, that expression looks like this. Now, that's not the most common form. We're used to this expression. Force, or more specifically, net force, is equal to mass times acceleration. It's important to remember that this is a vector expression. Force is a vector quantity, mass is a scalar quantity, and acceleration is a vector quantity. And of course, when it comes to analyzing, we can't mix forces in different dimensions, so we need to look at the component expressions for Newton's second law. And so the net force in the x or horizontal dimension is equal to mass times the acceleration in the horizontal dimension. The net force in the vertical dimension, also known as the y component, is equal to mass times the acceleration in the y component. And then lastly, the net force in the z component, that would be the dimension that's coming out of the screen towards you, is equal to the mass times the acceleration coming towards you or away from you. And of course, we get the net force by adding up or summing all the forces in that dimension, whether it be x, y, or z. So the important thing to remember here is that resultant forces must be broken into their components so each dimension can be analyzed separately. You cannot combine vertical forces and horizontal forces. So here's our little force. And so to analyze this force, we need to break it into its vertical and horizontal components. For the rest of this podcast, I'm going to just be talking about forces in 2 dimensions and not 3 dimensions. The SI unit of force, well, if force is equal to mass times acceleration, and we know the unit of mass is kilograms and the unit of acceleration is meters per second squared, then it stands to reason that the unit of force is kilograms times meters per second squared. And of course, we have a special unit called the Newton to represent that. But we need to remember that 1 Newton is equal to 1 kilogram times meter per second squared. Okay, let's talk about weight. Weight is the force of gravity acting on an object, and it is a scalar quantity. In other words, it's the magnitude of the force of gravity. And we calculate weight using Newton's second law. Since it's a magnitude of a force, it is mass times the acceleration due to gravity. Technically, it is the mass times the magnitude of the acceleration due to gravity. In other words, weight is a scalar, so if your gravity happens to be in the negative direction, it's not going to turn weight into a negative quantity because weight has no direction. Now, especially in college and AP texts, including the AP exam, you're going to see not the acceleration due to gravity, but you're going to see lowercase g. Okay, so you'll often see that weight is equal to mass times the gravitational field strength. So lowercase g is defined as the gravitational field strength. It is a scalar quantity. Now that's different than how I treat it in honors physics. I tended to treat it as a vector, the acceleration due to gravity. But gravitational field strengths do not have, they're not vector quantities, they're scalar quantities. And on the Earth's surface, g is 9.8 meters per second squared. On Moon's surface, g is 1.6 meters per second squared. And of course, The gravitational field strength depends on the planet or moon you're referring to, and also how far you are from the center of that planet or moon. So just a note here, you will not, in college texts or AP information, including AP exams, you will not see G with a minus sign in front of it. They are referring to the field strength, which is a scalar quantity. Also, you can, in most instances on the AP work, approximate G on the surface of the Earth as 10. Certainly you can use 10 meters per second squared when working on the multiple choice problems. So let's take a look at some force diagrams. So if we had an object and we had something pulling it at an angle, there'd be a normal force created by whatever the object's resting on, and of course a force of friction and the force of gravity. That's how I would have shown you how to do this in honors physics. Now, in the college texts or AP exams, you're going to see a little different notation. You're going to see lowercase f for friction. You're going to see capital T for the tension force, capital N for the normal force, and W, or sometimes you'll see the expression M times G, meaning the force of gravity. Okay, so don't be thrown off by those symbols. This is exactly how they map into the way you were taught in honors physics. Okay, let's talk about apparent weight. So apparent weight is the weight we feel. For instance, when we're riding on an elevator, we don't always feel our normal weight. Sometimes on the ride we feel heavier than normal. Sometimes on the ride we feel lighter than normal. The same is true when we're riding a roller coaster and going up and down hills. Sometimes we feel heavier, sometimes we feel lighter, and sometimes we feel the same as we normally do. So here's the reason why we have apparent weight. We cannot feel the force of gravity. Okay, we may think we can, but we can't. So not that you would do this experiment, but if we jumped out a second floor window, so please don't do this experiment, but if we jumped out a second floor window, as we were falling, the force of gravity would be acting on us, but we would feel weightless. We wouldn't feel anything. And that's because there's no normal force pushing up on us. So what we feel is the normal force of a surface pushing against us. So that's important to understand, that apparent weight is what we feel. So apparent weight is actually the normal force of whatever surface is pushing up on us. And of course, apparent weight is a scalar quantity, so we're talking about the magnitude of the normal force. At equilibrium, that means the normal force is equal to the force of gravity or weight. And by equilibrium, I mean that we have no net forces, no acceleration. However, for accelerated motion, we know that the normal force plus the gravity force has to be equal to mass times acceleration. So these two are no longer going to be equal in magnitude. The magnitude of the normal force is going to be equal to the magnitude of these two vector quantities, mass times acceleration minus the force of gravity. Please note this expression is not the same as taking the magnitude of mass times acceleration and subtracting from it the magnitude of the force of gravity. So don't fall into that mistake believing that this is the same as that. You have to actually do this vector subtraction and then take the absolute value to get the magnitude. So let's take a look at summing up what that means. If acceleration and force of gravity are in the same direction, then the normal force, or the magnitude of the normal force, is going to be less than your weight, and you're going to feel lighter. On the other hand, if acceleration and force of gravity are in opposite directions, then the magnitude of the normal force is going to be greater than your weight, and you're going to feel heavier. Finally, if the acceleration is equal to the force of gravity, both in magnitude and direction, then the normal force is going to be zero and we will feel weightless. That is why astronauts orbiting the Earth feel weightless. It's not because there's no force of gravity acting on them. We know there is. It's just that they are accelerating. It's centripetal acceleration, but their acceleration around the Earth is equal to the acceleration due to gravity, and they feel weightless because they're continually falling. Now let's talk about problem-solving strategy for force problems in general, and specifically Newton's second law problems. So first, draw a simple sketch of the scenario. You need to understand what's physically going on. Next, draw a free body diagram, also known as a force diagram, of the forces acting on an object. If you're dealing with a system of multiple objects, you need to draw a free body diagram for each object. Next, establish a convenient coordinate system, remembering that usually the x-axis is parallel to the surface. So if you're studying something that's on a sloped surface, you're going to need to rotate your x and y axes. Break forces not lying on an axis into their components and show these components, the x and y components, on the free body diagram. Analyze the x-axis forces separately from the y-axis forces, and then establish governing equations for each axis that allows you to solve for the desired unknowns. For instance, you may have acceleration along the x-axis and you may have no acceleration along the y-axis. So that will give you two different equations that govern the motion. And finally, you may need to use a system of equations to solve for multiple unknowns. And finally, as with all problems, review your answers to make sure that the direction and magnitude make sense. Again, this will prevent us from falling prey to simple calculator errors. You should be able to, without the use of your calculator, understand and know what direction the force should be in, and also approximately what its magnitude should be. So again, review your final answer against your conceptual understanding of the direction and magnitude of the force. Well, this ends our podcast on Newton's second law. I hope you found this helpful. Bye.